Hi all and welcome to my YouTube channel. Today we are going to be learning about the concepts of holographic communication. So what is a hologram? It is a technology that creates three-dimensional images using the interference of light beams to enable real-time immersive interactions. To make things simple, let us imagine holography as a kind of magical camera that doesn't just take flat pictures but creates a real life version of an object that you can almost touch. So, how is this hologram generated? Imagine you have a flashlight, but instead of a regular one, it's a super special light called a laser. This laser beam is very neat and focused like a perfectly straight beam of light. We shine this laser onto an object like a toy. The light bounces off the toy in all directions, carrying information about how the toy looks, its shape, color, and texture. When the laser light bounces off the toy, it creates patterns of waves, kind of like the ripples in a pond when you throw a stone. These ripples, in our case, the light waves, are captured on a special screen or a film. But here's the trick. Another laser beam shines directly onto this film at the same time without bouncing off anything. These two laser beams, one carrying the toy's light waves and one plain one, meets the film and creates a pattern. This pattern is called an interference pattern. It looks like a mix of swirls and lines, but it's actually the secret recipe for the hologram. Later, when we shine another light through the interference pattern, the pattern bends the light in a way that recreates the toy not as a flat picture but as a 3D object. Now we can see the toy from different angles as if it's really there in front of you, even though it's just made of light. So let us take another fun analogy. Let's pretend we are baking cookies. The dough is like the light bouncing off of the toy, full of details. The cookie cutter, that is the interference pattern, presses into the dough and captures the shape of the cookie. Later, when you bake it, that is, shine the light through the pattern, the cookie pops out, just like the hologram of the toy appears. So, have you seen holograms? Yes, we have. Have you ever noticed a shiny sticker on your notebook or credit card that looks like it can change when you move it? That's a very simple hologram. Now, how is the captured data transmitted? The data transmission is a critical component in holographic communication as it involves transferring vast amounts of complex 3D data in real time. This process must ensure minimal latency, high fidelity, and efficient use of bandwidth to deliver a seamless holographic experience. There are a few characteristics of the holographic data that is slightly different than the normal data that we see in our flat 2D pictures. It is significantly more complex. It involves point cloud data, color and texture information, and dynamic updates. What is point cloud data? It represents an object's 3D geometry and surface properties. A high resolution hologram may contain millions of data points. Color and texture information adds realism by encoding surface details like color, texture, and reflectivity. For real-time holography, data must be updated at high refresh rates. For example, 60 frames per second or higher. The challenge lies in managing this high data volume efficiency during transmission. Holographic data requires specialized compression methods to reduce its size while maintaining quality. Compression is essential in holographic communication because raw holographic data contains vast amounts of detailed 3D information that often exceeds the capacity of current transmission networks. Specialized compression methods are designed to significantly reduce the data size while retaining critical visual and spatial details. AI-based models leverage machine learning to identify redundancies in essential features in holographic data. They use advanced neural network architectures to achieve high compression ratios while maintaining the data integrity. The encoder decoder model is one of the most commonly used AI driven compression technique. How does encoder decoder model work? The encoder compresses the input data by identifying recurring patterns or structures within the holographic data. The latent space representation is obtained when the encoder reduces the data to a latent space that is a compact and abstract representation of the hologram's essential features. The decoder then reconstructs the holographic data from the latent representation, ensuring the output closely matches the original input format. Some of the key tools that are being used in this encoder decoder models are convolutional neural networks, variational autoencoders, and transformer models. AI driven compression is particularly effective for dynamic holographic scenes where the data's complexity evolves over time. By learning from data patterns, this method can generalize and adapt to different types of holographic content. Traditional compression techniques for 2D images like JPEG or H264 are inadequate for holography, which requires specialized 3D algorithms tailored to the unique nature of point clouds and holographic images. Now let us look at the different types of 3D specific algorithms. The point cloud compression or PCC follows three main steps. The first one is geometric compression, which reduces redundancy in the spatial arrangement of points. For example, points in flat surfaces or repetitive patterns are grouped or simplified. The second one is attribute compression. It optimizes the representation of color, texture, and other per point attributes, often by encoding only changes between frames. The last one is temporal redundancy reduction. In dynamic point clouds, successive frames are often similar. PCC minimizes storage needs by encoding only the differences between constructive frames. The high compression ratios with minimal quality degradation is especially useful for real-time holographic streaming. The next type is the wavelet-based compression. And how does it work? It uses wavelet transform, which decomposes holographic data into frequency components. Low frequency components, which capture the overall shape and structure of the hologram, are preserved with high fidelity. The high frequency components, representing finer details and noise, are compressed more aggressively. Wavelet based compression is excellent for preserving depth and light field properties of hologram. It also allows multi-resolution storage, which users can access varying levels of detail based on their device or network capabilities. The holographic communication uses a special transmission type called the progressive transmission. Progressive transmission techniques prioritize delivering holographic content in layers, starting with a basic version and progressively adding details. Let us now look at how progressive transmission works. The base layer contains a simplified, low resolution representation of the hologram, which is transmitted first. It also enables users to quickly see an approximate version of the hologram, providing immediate interactivity. The enhancement layers transmit additional details such as texture, color, and finer geometric structures. These layers incrementally refine the hologram, improving its quality over time. Let me now summarize the workflow of progressive transmission. First, a low resolution hologram is displayed to the user within milliseconds of starting the transmission. As more data packets are received, the hologram is updated to include finer details. After all the layers are received, the hologram achieves its full resolution and quality. These compression techniques address key challenges in holographic communication like massive data volumes, real time constraints, and scalability. Holographic communication depends on high speed, low latency networks to support real time transmission, like Ultra HD holographic streams can require up to several gigabits per second. Technologies like 5G and eventually 6G provide the bandwidth to accommodate such demands. Low latency is critical for real time applications like remote collaboration or surgeries. The target is under 1 millisecond round trip latency. To avoid interruptions, network must maintain consistent throughput and handle packet losses gracefully. Processing holographic data in real time places heavy demands on centralized servers. Mobile edge computing offers a solution by distributing computation tasks across multiple edge servers near the user. The key advantages include reduced latency, load balancing, and context awareness. Holographic displays are the culmination of the holographic communication pipeline where 3D images are reconstructed and visualized in real space. These displays use advanced optical technologies to create the illusion of depth, presence, and interactivity without the need for special glasses or headsets. Two prominent types of holographic displays are volumetric displays and light field displays. The volumetric displays reconstruct holographic images by projecting light into a physical 3D volume, enabling the visualization of 3D content from multiple angles. The volumetric displays work by projecting light onto a medium at precise angles and positions to form a 3D representation. By illuminating specific points within the display medium, the device creates a volumetric image visible as floating 3D object in physical space. A high-speed rotating surface displays a 2D slice of the 3D object. The rapid rotation creates the illusion of a fully 3D object. Some displays use acoustic or optical traps to suspend particles in air. These particles serve as points of light that can form a dynamic 3D image. It also uses voxel grids that are 3D pixels within a transparent medium. Lasers or LEDs excite these voxels to emit light, forming 3D images. Light field displays focus on recreating the behavior of light rays in a way that closely mimics the original scene, providing a more natural and immersive 3D viewing experience. A light field represents the intensity and direction of light rays coming from a scene. It includes all the light traveling through every point in space. Advanced cameras capture the light field data, recording the spatial and angular information of the light rays. Light field displays use micro lenses or layered screens to reproduce the captured light rays. The reconstructed light rays behave exactly as they would in the real world, creating depth perception. Since the displays reconstructs the light field, viewers can see the scene from different perspectives depending on their position, just as they would with real object. Real-time rendering is a critical aspect of holographic communication, enabling the seamless generation and display of dynamic 3D holograms with minimal delay. This process relies on advanced computational technologies and infrastructure to handle the immense data and processing requirements. Two essential components in this domain are mobile edge computing and AI assisted reconstruction. Mobile edge computing brings computational power closer to the user by deploying servers or processing units at the edge of a network, such as within local data centers or cellular towers. This decentralized approach minimizes latency and optimizes rendering performance. Holographic rendering demands immense computational power to process point cloud data or reconstruct light fields in real time. MEC offloads heavy computational tasks from user devices to nearby edge servers, allowing lightweight devices to handle holographic displays effectively. By processing data at the edge, that is closer to the user, MEC eliminates the delays associated with transmitting data to and from centralized cloud servers. This is crucial for applications like holographic communication, where even minor delays can disrupt the sense of immersion and presence. MEC systems also monitor network conditions and allocate resources dynamically to ensure smooth holographic rendering. AI plays a pivotal role in reconstructing high quality holograms on user devices. Lightweight neural networks process and enhance holographic data to maintain visual fidelity even in constrained environments with limited bandwidth or computational power. Holographic data is transmitted in compressed formats to reduce bandwidth requirements. AI models such as encoder decoder architectures reconstruct this data into high quality holograms. AI algorithms can detect incorrect artifacts or missing information in the hologram caused by compression or transmission errors. AI also adjusts the rendering quality in real time based on user device capabilities and network conditions. When MEC and AI assisted reconstruction work together, they form a robust system for real time holographic communication where MEC handles intensive computational tasks like real time data processing and network optimization, ensuring that data reaches the user's device quickly, and AI reconstructs the hologram locally, adapting to the user's specific device and network conditions while maintaining visual fidelity. Thank you for watching.